Thank you, Marcy, and welcome everyone back to part 2 of our series this month, where we're taking a look at a 2-story structure and designing that for high wind, high seismic, and snow loads. So on your screen you see 2 documents. This particular webinar does not have handouts, so Brian we'll be sending links to the resources page where you can download the workbook, which is the document here on the right, and you'll see workbook on the cover. So if you want to get that up in front of you, either on your desk or on your screen, that's primarily where we'll be today. The other document is called the Wood Frame Construction Manual for 1- and 2-family dwellings, and it's our ANSI standard that's approved referenced in the 2015 International Residential Code and International Building Code, and that's where we get all the tabulated values that we use for solving this particular design. So get those out and available. We'll be referring to those as we go, and while you're doing that, I'll have Marcy launch our first poll to find out who's with us today.
Absolutely. So let's see. First one's always the easiest. What's your profession? Architect, engineer, code official, builder or developer, and other. And as always, I usually give you about 30 to 45 seconds or 80% of the vote. And I'm actually going to cut these short today since we've got a lot of material to cover. So I'm going to close this and share. So we've got about 71% engineers, 19% code officials, 4% architects, and 6% other. All right. Welcome, everybody.
Okay. Great. Thanks. And so in your workbook, I'm going to have you jump right away to page 13, shown here again on the right. Part 1, we talked last week. We talked about the structure, the layout of the structure, the loads on the structure, and a lot more detail about the Wood Frame Construction Manual and the commentary that goes with that has all the background information. So we're not going to cover that ground again. It's available up on the website if you need to go back to refresh on that. So today we'll talk about roof and ceiling framing. We'll talk briefly about roof and ceiling sheathing. Then we'll talk about wall framing and connections of the roof to that wall system, and then a little summary at the end. So let's jump right away to the cross section of our roof system. And I'm going to point you first to this little icon up here in the top right. If you can see my pointer up here in the top right of the document, this always gives you an idea of where we are in the structure. And because this particular structure has a finished attic on one side and then a vaulted ceiling on the other, it's going to give us an opportunity to show a couple of different things about the manual that are helpful to you. We are going to design this as a rafter system. The spans here are probably about as we're going to max out just about any kind of lumber that you can get at a lumber yard. And we know that a lot of trusses and even i-joists are going into roof construction. Those are typically designed by others, and so to give you a sense of what you can do with these rafter tables for solid sawn lumber from the Wood Frame Construction Manual, we're going to design this with solid sawn rafters. So again, we know trusses are pretty common. But the other thing that we want to talk about and just clarify for folks who are on with us today is the difference between a collar tie and a ceiling joist or a rafter tie. So these collar ties that you see up here at the top of the peak of the structure are used to resist wind uplift and to keep those rafters from pulling apart at the ridge. The ceiling joist, and what we'll see in a second with the vaulted ceiling is a rafter tie, are used to resist thrust. You see the arrows here at the top plate at the end of each rafter, and so those tie the walls together to resist that tension load that you're going to get when you get the snow load on the roof system. So collar ties are for wind loads, rafter ties and ceiling joists are for that outward thrust. So as we talked about earlier, these are the typical, these are the dimensions for this system that we're designing. It's a 32-foot span, so we're going to divide that up in half and have 16-foot joists on either side of an interior wall below for that finished attic space. We've got this opening here in the diaphragm that we talked about last week that goes all the way up into that attic space as well, but it meets the limitations that allow us to design that diaphragm. So that's our roof, rafter, and ceiling framing plan. And we're going to start at 16 inches on center and adjust as necessary if we need to. And so now jumping to page 15, you see a similar detail in the upper right, which means we're now looking at that vaulted ceiling. The difference here is this rafter tie is raised about 1/3 up into the attic space, and that's going to create some additional moment on these rafters that we need to account for. We can do that with the tables, and we'll talk about that. One of the things I want to point out, though, is that, again, we've got rafters and rafter ties at 16 inches on center. I think I'm actually going to correct that in this workbook because, as it turns out, we're going to have to go to 12 inches on center to get these to work because of that additional thrust here due to pulling that rafter tie up into the lower third of the span here. And so you'll see that in a second. But again, we started at 16. That didn't work, so we're going to end up going to 12 for this particular span. Also note this span here for the ceiling joists, because it's raised, is 21 feet. So we'll need to design to account for the tension and live and dead loads there as well. So we'll look at that as we work on through. So on page 16 then, this is the section of the wood frame construction manual, 3.5.1.1, that kind of gives you chapter and verse about where you go to find the right table. And in this particular case, we're looking at tables 326B and in 326E. So there's a typo here that I want to point out to you right away. From the last draft, I think, or the last version, we had 326D. This one should be changed to an E. So if you've got a copy there, you want to mark up there and there. We're going to be in table 326E. For rafters, we're going to look at live loads, wind loads, and snow loads. So we're going to have to evaluate all kinds of different loads on a rafter. It's not just a matter of picking a snow load, and in our case, it's 30 pounds per square foot, and pulling that out of a table and saying we're all good. When you're in a high wind zone like we are, which is 160 mile per hour exposure B, that means you're going to have to check some other things as well. And so because we have a ceiling on this one, in this finished attic, we're going to use an L over 240 deflection ratio. And I'm going to go ahead and jump right to the table 326B over here in the wood frame construction manual. So if you have that out in front of you, take that out, and let's then get over to table 326B. Sorry, I got to click through this here quickly. So when you get to these tables in the wood frame construction manual, we've got some help here in the upper right-hand corner. So first of all, we're going to look at the live load, and so that's 20 pounds per square foot. And then we mentioned the L over D ratio of 240. So pay attention there. Make sure you're in the right table. And we're just going to look at the Doug fir larch number 2 at 16 inches on center. So pretty easy look up, 16 inches on center here. Our dead load's 10 pounds per square foot shown here. In this particular case, since it's a live load, we're going to try a 2x8. And let's see, what does that end up giving us? 326. be down here. Sorry, I was in 12 inches on center. Jump down here to 16 inch on center field, and you see that that gives us a span of 18 feet 5 inches. So you see how the tables are set up to pull spans quickly out for different load configurations. Pretty straightforward. But there are adjustment factors. There are footnotes. So I'm going to jump to the footnote at the end of this table. So we're going to have to scroll through quite a few tables here to get to the footnotes at the, or no, just in this case, it's only two pages. So page 288 of the wood frame construction manual, you see the footnotes associated with that. And for a live load situation, we need to make sure that we're looking at footnote 2. And this is from ASCE 7 that allows you to take into account a sloped roof adjustment factor. And so for our 7 and 12 roof pitch, which is what we have on this structure, you can take that sloped roof adjustment of 1.05 with a 10 pound per square foot dead load. So I'll jump back to the workbook now real quick so you can see how we've done these calculations. Now over here on the workbook on page 16, right under Doug Fir Larch, number 2, 16 inches on center, we had a 18'5" span, but we can actually bump that up to 19.4. It's plenty more than we need for the 16-foot span that we have to do, and that's obviously a horizontally projected span. So that's a pretty simple approach for a live load calculation. Now, back to the workbook, and since we're here in these footnotes, footnote 3, pretty slick. It allows you to actually do your wind load design based on that live load span. So take a look at footnote 3, bottom of page 288 for 160 miles per hour. Make sure you're in the right exposure. We're exposure B. And jump down here to a 7 and 12 roof pitch. We're going to work our way across, and we end up having a factor of 0.95. So that is what we will then use, and it's cumulative with that other adjustment factor that we looked at earlier. Jump back to your workbook on page 16, and we have 2 adjustment factors here to determine your wind load span. So it's the 0.95 wind factor and the 1.05 sloped roof adjustment factor. We're still okay. But note, your higher pitches, 12 and 12 pitch, for example, over there in the wood frame construction manual has a 0.68 factor. So there are going to be cases where you've got a steep roof, it's like a big sail on a sailboat up there in the wind. It's going to put a lot higher wind load, a lot higher bending load on those rafters. So you could get into a situation where wind load would actually control potentially for some of these applications, depending on the pitch, depending on your wind load, depending on your exposure category. All of those things sort of work into wind design. So again, for you engineers in the audience, we've done the math from ASCE 7 for you, and so it's a pretty quick check for wind load design of a rafter system that you've got here at your fingertips. Now the easy one that you're probably all accustomed to then is a snow load span, and so we're going to now jump to 326D. So back in the wood frame construction manual, let's scroll down to 326E. Sorry, it was a typo in there. I apologize. I think it's because we changed that L over D ratio to 240 with this version. So table 326E, and we are now going to need a 2x10 to make this one work at 16 inches on center. We're going to come over here and look at a 2x10 Doug Fir at number 2 grade, and it's 18'9" span. We don't have that thrust factor here because this is just a regular ceiling, just has a regular ceiling joist on it. So that span also works, and because we bumped up to a 2x10 back in the workbook, that's what's going to control in this particular application. So note here that 2x12s might be needed for bat insulation, some energy requirements. We're going to see in a second we're going to need it for those for that vaulted ceiling. Next thing we want to look at down here at the bottom of the workbook, page 16, are ridge beams. So if you decided instead of a ridge board application you wanted to span, I think it's 25 feet that we have here in this particular part of the roof with a ridge beam, you can do that. So jump back over to the wood frame construction manual and scroll to table 329. 329 is your ridge beam spans. And you can see here that you've got both solid sawn built up members and glue lam down here at the bottom. We can make a 3 1/8 inch by 24 inch glue lam work, or we can make a 5 1/8 by 19 1/4 work. And you have to interpolate over here in this table. We won't go through that right now, but again, would allow you to do that. We've got some notes down here at the bottom of page 16 in the workbook. Back over here on the right-hand side shows that ground snow load that we looked at and the span that you can get. Now, also note that if you decide to go this route, you've got load path issues. So you would have to make sure you've got built-up columns underneath of the ends of those ridge beams to take your load all the way down through both floors into the foundation system. So it's not just a matter of throwing a ridge beam up there. You've got some other load path to design in. That would have to be done by engineering analysis. So we don't have those built up column tables in the wood frame construction manual yet. We've been asked about that. We may get something like that at some point, but right now that's what we've got. So page 17 then of your workbook, what I want to do now is take a look at the raised ceiling. And I know we're clipping through pretty fast here, but again, take a look at this diagram up here in the top right. You see that we're going to look at that vaulted ceiling. It does also have a finished ceiling with gypsum, but the difference here is we've got a rafter tie a third of the way up into the attic space. So we're going to jump back over here in the workbook to the footnotes in table 326, in this case 326E. I think that'll be the easiest way to get us the answer that we're looking for here. So everything's identical in this example except for this thrust span adjustment factor, and that's going to be in footnote 1 to table 326D. I think it's also the same footnote in the other tables as well. But let's jump over there to that footnote, and what this footnote allows you to do is to account for the additional moment. We talked about the tension loads that end up here, and again I'm in the wood frame construction manual, page 299, and we're 1/3 of the way up into the attic space. Sorry, that doesn't do well. Gives us a 0.67 factor. And again, that's accounting for additional moment that's put on those rafters when you raise it up into that attic space. So again, we've done a lot of the math here and made it a pretty easy calculation for you. You come back over to the workbook, bottom of page 17, we're going to apply that 0.67 factor here to the snow load application. We're actually going to apply it to all of them because that additional moment is going to be there no matter what. So that gets applied to live, wind, and snow load applications here in this table. But what you see happen is that we had to go to 12 inches on center with a 2x12 to get that one to work. So there's the ramifications of a raised ceiling in a attic space like that. We've got some notes down here at the bottom about ridge boards. Per the IRC code, you can go with a ridge board rather than a ridge beam, and so we're showing how that would work as well. So we're going to keep moving along here. We're going to skip past ceiling joists. That's a pretty easy lift for just pulling numbers out of a table, but I'm going to have Marcy, if she would, come back and take us through our next poll.
Absolutely. So roof rafters are designed to resist all loads except which of the following? wind, snow, live, or seismic. So everyone is very fast here. That's great. So just a little bit longer. Alrighty, I'm going to go ahead and close the poll and share it. So 89% said seismic, 8% live, 2% wind, and 1% snow. And I'm going to let you, buddy, say what the real answer was.
Okay, so yeah, we're checking these rafters for live wind and snow load, so not seismic. And so everybody's paying attention, and we'll keep on moving. So as I mentioned, we're going to skip past the ceiling framing. That's pretty easy. Look up tables there. I will point out down here, however, for the floor diaphragm bracing. So down here at the bottom of page 18, per the Wood Frame Construction Manual 3.3.5, in order to get the wind loads from the gable end wall into the floor diaphragm, and in this particular case we've got a attic space that's got a floor system. So once you get above 130 mile per hour wind loads, it's going to require blocking at 4 feet on center, like shown up down here in this detail, in the 2 bays. And again, that just stiffens up the end of that diaphragm to get the loads from that gable end into the floor diaphragm so that it can be shared then into the shear walls. So just note there is some prescriptive application there for those diaphragms. And that reminds me, I'm going to jump back there just one more time to talk about that. That you may have already figured out then that the diaphragm values we're assuming are unblocked diaphragms. So this blocking then just above 130 just gives us a little bit of added stiffness to get some loads into the shear walls. So again, the commentary gives you background for all the assumptions, including the diaphragm capacities that we assume in this document. So let's jump on then to the next page, on page 19. Did a little bit different twist here in sizing the ceiling joists per chapter 2 of the Wood Frame Construction Manual. So in this particular case, you're looking up the bending and E value that's required for this 21-foot span joist, and then you'd look up design values in the NDS, or the NDS supplement rather, tables 4A and 4B, based on those required E and bending values to come up with, in this case, 2x8 number 2 works for all those ceiling joists. And again, just kind of gives you a little bit different approach for how you can size those per chapter 2, the engineered provisions of the workbook. Page 20 of the workbook then, we're talking about roof and ceiling sheathing. This is to deal with suction loads. Let me just see if I can jump back here in the Wood Frame Construction Manual to table 2.5, and we'll talk just briefly. Sorry, 2.4. You don't have to turn there, but if you can see it on your screen, you can see that the suction load, or the loads on these structures, are going to be higher around the edges, whether we're talking about the roof or the wall systems. And so that's all built into the tables that we're looking at, whether we're talking about suction or other loads on the walls and roof systems. So just remember that they're going to be higher around those edges, because we'll talk about that as we work our way through this workbook. So we've taken care of the suction loads on page 20. Roof diaphragm bracing per WFCM 3.5.5 says that, and there's an exception there that says that you can omit roof diaphragm blocking if the floor is used to brace that gable end wall. And so we've already done that back on the last page when we looked at the floor diaphragm. So if you just had a ceiling system you might need to block the rafters, and we'll look at that in a second, but we've actually blocked, at least on this end of the building, the end that's got the attic space, we've already blocked the floor system, so we don't need blocking in the rafters. You'll see in a second how we design that vaulted ceiling, the ceiling joist, as an alternate to blocking the rafters. So just stay tuned and we'll get there in just a second. Oh, that's coming up here right on the next page, page 21. So, and again, where we're looking at the vaulted ceiling over here on the left-hand side of the building, that raised ceiling, we can, because we don't have, because we don't need to use that ceiling as design it as a diaphragm. If we block in the first 2 bays at 4 feet on center in the rafters, that is appropriate for, again, getting the loads out of the gable end into that roof diaphragm. But the alternate down here under the or is that we can design an attic floor or roof ceiling system to act as the diaphragm and take those loads. And so that gets us into table 315 of the wood frame construction manual. So jump back into the manual. If you're following along in one of your books, jump back to your wood frame construction manual, table 315. Make sure you're in exposure B, and you see we've got the table set up here for both wood structural panel sheathing on that ceiling diaphragm, or for gypsum down here at the bottom on the diaphragm. And you see the tributary area here shown in the picture in the graphic. That's the load we're trying to resist. And so for 160 miles per hour, 712 roof pitch, we work our way across, and this is actually a 21-foot span, so we'd have to interpolate between 12 and 24 feet, and we end up somewhere between 4 and 8 feet for the wood structural panel sheathing, and then down here for the gypsum, we end up somewhere between 10 and 21 feet. So back to the workbook, page 21, you see that we've actually solved this here for we interpolated 7 feet and about 18.5 feet. I'm not going to take time to jump into all the adjustment factors, but in your wood frame construction manual, take a look at the adjustment factors at the end of the table. Those have to do with whether you're bracing one or both ends of the system, the wall height adjustment factors, a ceiling framing adjustment factor. So there are footnotes that apply. We've applied those here back in the workbook, and what we end up with is an adjusted value of 15.9 feet that's required for gypsum, and we don't have that much. In this vaulted ceiling, we've only got about 14.5 feet. So gypsum won't actually work to brace that ceiling. We'd have to go to a wood structural panel or go and block the rafters like we've shown here per the prescriptive provisions. So you get a sense of how this works. You've got lots of options for getting those loads into the diaphragm, blocking in the rafter system, or using the ceiling as a diaphragm to get those loads in. So this shows both those options, and you can kind of work through those on your own as well. So I'm going to have Marcy come back and get us another poll question in.
Okay, here we go. So per the WFCM, roof diaphragms can be braced with blocking between rafters in the first 2 bays, attic floor ceiling and sheathing, metal strapping, or A and B only. Not sure what happened with the alignment there, but
that's okay. I think we can. Looks like everybody's got it. So.
Okay. All right. Let's go ahead. So I'll close it. Share it. So I'm assuming that you said everybody's got it. It's A and B only. So.
Yes, and that's good. I'm glad you all picked that up. So those are the 2 options. Now, what if anybody, and I don't think anybody, well, yeah, a couple of people picked the metal strapping. Let me just talk briefly about this figure down here at the bottom of the page page 21. So this ceiling bracing gable end wall detail, we do show some metal strapping there, but that's really to resist the wind loads on the leeward edge or leeward side of the building to keep that gable end wall from blowing out. So this detail here is another prescriptive detail that if you've got a wall system and say a set of trusses or some framing on top of that wall system in the gable end, what we saw after a lot of hurricane evaluations is that those end walls got blown out because of improper detailing here. So this detail comes from figure 3.7a of the wood frame construction manual. It does show some metal strapping, but that's just to get that's to resist the leeward wind loads. The windward loads are going to be handled by blocking or roof diaphragm bracing, either with gypsum or with wood structural panels. So hopefully that makes it pretty straightforward. So we're going to now jump to page 22 of the workbook and get into some wall framing discussion here. So let's look at the non-load bearing walls first. And the first one, again, you see these little figures up here in the top right. We're going to look at that little area at the gable end wall where we've got that raised ceiling. So this is the end where we've got the vaulted ceiling. So we've got a couple of options we can use here that you see spelled out. One, we can balloon frame. Sorry about that. We could balloon frame from the second floor all the way up to the ridge, and that's about an 18-foot height there. So we'll try that, see if it works. Or we could just put some studs up about 12 feet up to where that raised ceiling is, and then frame above that with about 6 feet of gable end studs and design those. So when we look at wall stud design, if you want to turn there in your wood frame construction manual, to table 320 A. Let's see, we're at H over 180, exposure B, so we're on page 232 of the wood frame construction manual. So let me just talk again primarily to engineers in the audience about how we're designing studs in these systems. Now this is a non-load bearing wall, so hang on, let me hold that discussion here for just a second, and we'll get to that when we talk about the load-bearing walls. So let's look at designing these gable end walls. We are designing with component and cladding wind loads on this gable end wall. So we go in here and as it turns out, we're going to have to go in at 12 inches on center to make this work for an 18-foot long stud, as you might imagine. Let me jump to page, sorry, I told you wrong. Let's jump to page 233 because the wind loads span across 2 pages, so we can get it all on opposite pages. So 233 under 160. We're going to jump down here and again look at a Doug fir larch number 2 because it's the first one in the table. And let's see, 12 inches on center, Doug fir larch number 2, and it's a 2 by 6. Why is that showing 19.5? 19.5. Sorry about that. I actually went through this before I started to make sure I was getting the right answer, and I'm sure some of you are screaming into your screen, "It's a different page, you idiot!" And Lori or Pete, if you're seeing what I'm doing wrong here, you can jump in too. But I'm not pulling that 19'5" span for some reason in the table here. All right, so I think I do know. Let's see. This is B, table 320B, because this is minimum sheathing materials. Okay, good teaching moment here. All right, so we've got two different types of tables. These are minimum sheathing tables, which means we're only looking at having gypsum on as a blocking or as a bracing type material. So I'm actually needing to jump to the next set of tables, which is going to be 320B1, and that has 3/8 wood structural panel sheathing on the exterior. So I didn't catch that there in the workbook, but we do say either A or B. Because we know we're going to have wood structural panel sheathing on the exterior, we need to be in the table that has 3/8 inch wood structural panel sheathing on the exterior. So we're exposure B, H over 180, 3/8 inch wood structural panels, and so that one even caught me off guard. Sorry about that. So under 160 mile per hour wind load, Doug Fir Larch number 2, we're at 19.5, which is the number we have in our workbook. So sorry about kind of rattling around to get there, but that's where we need to be. So we'd see that we could make an 18-foot span work. That's probably not too practical because, as you see in the table back here in the workbook again, as soon as we get away from the ridge a little bit, we could actually drop that down, within 4 or 5 feet on either side to something like 16 inches on center. We could double up the studs there, I guess, if you want to balloon frame that all the way up. Probably a better solution here, option 2, is just to frame it 12 feet, and that makes it a little bit easier to frame at 16 inches on center. So I'm going to jump to page 23 of the workbook, and again, using the tables, and we won't jump back into those tables, but we're in a similar table. If we do the lookup, we see that a 2x6 number 3 actually works instead of going to a number 2 grade or a higher grade. And at 24 inches on center, that works. Now, back in the workbook, in the wood frame construction manual, let me just jump to the footnotes. So if you're following along in the wood frame construction, let's jump to page 258. I want you to look at footnote A, because this is a pretty important footnote, and this can catch you sometimes too. But remember, we talked about the higher loads in the end zones and edge zones. That also applies on walls like we have in the wood frame construction manual. And so what we've got here is a footnote that indicates that you have to multiply the spacing by 0.8 in those end or edge zones. So I designed using the lookup tables at 24 inches on center, knowing that I've got that 0.8 factor to apply. Again, you could drop the spacing down just at the edges to 16 inches on center or 12 inches on center if you design it the rest of the wall for 16. You could double up studs in those areas, but you do have higher loads in those end zones. So just know going in that you have to make that adjustment one way or the other. So the other thing that you need to be aware of and you need to look for is that there's a maximum load for gravity loads that we have to account for as well. So we're going to jump back into the Wood Frame Construction Manual, Table 320C on page 258. And this table is taken right out of the IRC. And the reason we do this is to make sure it's kind of the catch-all for the maximum heights and spacings for different studs in the system. For the non-load bearing studs, which we're looking at here, we see that we can go as high as 20 feet with 2x6 studs, and we can go 24 inches on center. Now, if you've got 2x4 studs, you can only go up to a maximum of 14 feet, and that just has to do with the L over D ratio of the studs, maximum L over D ratio of 50. So back in our workbook, that's why you see we've got this sort of overarching catch here. You can't, you still have to check to make sure you don't exceed any IRC limits. So that is the other table, 320C. that you got to check. Make sure you've covered that. All right, so page 24 then of the manual, we're going to move on into connection design. And just a heads up, we'll probably go right up to the top of the hour with connection design since we've got a lot of territory to cover, and then we'll do some Q&A at the top of the hour. So if you can stick around 10 minutes after, we'll do some Q&A at the end. So page 24 of the workbook, and we're going to look at lateral framing and shear connection. So we're going to attach the roof assembly to the wall assembly, and so this is where we're looking at the load-bearing walls below, and we're going to now jump to table 3.4a in the wood frame construction manual. So back to the wood frame construction manual, if you've got it, and open that up, scroll to those tables, and I'll tell you in a second why we're jumping to 3.4a rather than 3.4, but make sure you're in exposure B, and for 160 miles per hour, and we're going to assume 16 inches on center, and over here under 160 we see that 3 nails works at both 8-foot and 10-foot wall heights. Our wall heights are actually 9, which means we have to interpolate, but back in the workbook we see that those 3 nails work. And so what we've done here in this table is that we've checked both lateral and shear. So that's all done and spelled out for you in the commentary. You can go take a look at that. Whichever one controls then is what we use for the solution here in this table. And so you can see the detail here that shows attachment of those rafters and ceiling joists into the top plate to resist lateral and shear loads. Now we are going to have to look at the uplift loads as well in just a second, but let's just stick with the lateral and shear for now, and we're going to jump to table 3.5a. So to take care of the non-load bearing wall assemblies, so over in your wood frame construction manual, 3.5a, page 182, exposure B, 160 miles per hour. We jump down here again, we see 16 inches on center works for our wall height of 8 or 10 feet, 2 nails works there. The reason I only checked 16 inches on center, if you notice, we did have, I think, 12-inch on center rafters in that vaulted ceiling, but if it works for 16, it works for 12. So just note that as well. So we just checked 16 knowing that 12-inch on center would work. And there are some adjustment factors. Again, check all your footnotes. I'm back in the workbook now, bottom of page 24. There were a couple of footnotes that kicked in again for framing at the corners. You have to constantly be looking to see what the assumptions are for the various connectors. So so that takes care of our lateral and shear loads. I'm going to jump now to page 25 of the workbook, and we're going to look at our uplift connectors. And to do that, we're going to jump to table A-3.4, which is actually an appendix table, and that's because we moved the straps. A lot of those straps are proprietary products. We moved some of the proprietary products to the appendix chapter, but we still maintain those. And so here in A-3.4, you see you can size the minimum number of 8-penny common nails at the end of your straps. So for 160 miles per hour, 16 inches on center, we come down here and we see that, I'm sorry, for the roof span, of 32 feet, I believe it is. we come down here and we see that we're requiring 4 nails at the end of each strap for that. So pretty easy. Look up tables, and you can see none of the footnotes kicked in here. Back in the workbook, though, I just want to point out this note to you, and note that over that vaulted ceiling, again, we're at 12 inches versus 16 inches on center, and to make sure that load path is maintained, we're going to want to make sure that we've got these twist straps in there, so that the straps, if they're not, if they're coming across the top of the truss or whatever rafter, I know this is showing a truss, but it could be across a rafter, that you've got load paths so that those are coming down into the sheathed side and of the assembly, and that you're not creating any kind of eccentricity here by putting that strap on the inside. So just make note of that as well. That's spelled out for you in the wood frame construction manual. All right, so jump into page 26. So what this table does, and again, back to you folks that want to just determine what are my loads on my load-bearing and non-load-bearing walls. So far I've showed you prescriptive solutions. Let's jump now to table 3.4, which actually spells out the loads on these various in these various areas. So page 170 in the wood frame construction manual, page 171, sorry, so I can get to the 160 mile per hour wind load. Page 171, exposure B, you can see that we tabulate uplift, lateral, and shear loads. And so back in the workbook, and again, because we're a little short on time, I want to make sure we cover everything. I just want you to note that, for example, pulling an uplift load value out of I'm sorry, this is for the load bearing tables, wall connections. Yep. So if you were to use that table 3.4, come up with an uplift value of 479 pounds, apply whatever adjustment factors would be required for that, then you can also pull your lateral and shear loads. But again, we've done a lot of that for you already in the prescriptive tables and showed how many nails are required. This would be if you want to pull some hardware out of a catalog, it lists the capacities that would be required per the catalog. Same approach for non-load bearing, and that would be from table 3.4C, where you can actually pull those capacities right out of the table. You can see here on page 178 of the wood frame construction manual that those capacities are tabulated as well. So back in the workbook, jump into page 27. Sheathing and cladding attachment. Again, we have to make sure we handle all the suction loads on the roof system, and we talked about that earlier. And where you've got higher loads on the edge zones as opposed to the interior zones, you can see our solution here based on our lookup table 3.10 at those 4-foot perimeter edge zones. The nail spacing for 8-penny commons is 6 inches on the edges and 6 inches in the field. So where you would normally do a 12-inch nail spacing on the intermediate studs or rafters, rafters in this case, you have to go to 6 inches on center in this particular example. The interior zones away from the edges, you could go with that standard 6 and 12 spacing, but look what happens out here on the gable end. Gable end rake with the overhang has 4 inches on center spacing, and that's per some of the prescriptive details. And you can see that over here back in the workbook, in the wood frame construction manual, table 3.4C, the detail at the bottom of the page here. You can see that the connections are prescriptively spelled out as 4 inches on center. So higher loads at the edge of the building need to be accounted for. Back in the workbook, let's take a look at ridge straps as an alternate to collar ties. So if you were to read WFCM 3.2.6.1, you'd see that rather than using the collar ties on the inside, if you wanted a true vaulted ceiling, went all the way up to the peak, where you could run your gypsum all the way up to the peak, you could go with ridge straps across the top of the roof, as shown over here in this diagram. And to do that, you go to table A dash 3.6. So again, back in the wood frame construction manual, we've tabulated those for you. Exposure B, our 7 and 12 roof pitch down here. See how many nails you'd need for that 32-foot roof span. It ends up being 3 nails on each end. Now that's dependent on your rafter spacing. And so back in the workbook, you see there's a couple of footnotes that kick in down here at the bottom. And so there is a 1.33 adjustment factor if you're at 16 inches on center. So it actually is 3 nails, 12 inches on center for the vaulted ceiling, 4 nails for the 16-inch on center spacing for the rafters. So pay attention to the footnotes. Can't stress that enough. Pay attention to the footnotes. All right. Jumping then to the next page, page 28 of the workbook. And Marcy, I may have missed a poll. I'm sorry about that, but we're kind of running short on time, so I think I'm just going to keep on going here so that we have so we can make sure that we finish up on time.
Sure.
Okay, so we talked about ridge straps just a second ago. Alternatively, back in table 3.6 of the wood frame construction manual, there is a table that allows you to calculate the capacities of those ridge straps. If you're using a proprietary connector or pulling values out of a catalog, you can see, jumping down here to the 7 and 12 roof pitch, a 32-foot roof span, we end up with 350 pounds of capacity. Again, the footnotes down here, footnote 3 in this particular case, shows that our default is 12 inches on center. And so at 16 inches on center, we'd bump that up by 1/3. So back in your workbook, you see where that 1/3 factor is coming from, and so you see what the loads end up being on that structure or on that particular connecting device as well. All right, so moving on page 28 of the workbook, table 3.1 of the wood frame construction manual is sort of the catch-all. So I'm going to just close up the bookmarks here so we can get a little bit better look at table 3.1, because you'll want to refer to this one often, maybe bookmark this one, or put a sticky tab in your wood frame construction manual. But this is sort of the catch-all nailing schedule for throughout the document. You can see it has some similarity to what's shown in the IRC. Let me blow that up just a little bit more. And what you can see here in this table is, for example, the very first entry talks about rafter to top plate connections. It's going to show you exactly where to go, what table to refer to get those connection values. Ceiling joist to top plate, same thing. Now, there may be some sort of blocking to rafter details, for example, here, where you don't really need a table. We've just tabulated the number of 8-penny common or 10-penny box nails that you need for blocking the rafters, blocking in the rafter systems that we talked about. And so look here for those details to make sure that you get, again, a complete load path and that you're detailing everything appropriately. So back to the workbook. Let's see here. Ceiling joist to parallel rafter. So that directs us to table 3.9a. So Let's jump there in the wood frame construction manual. All right, so we talked earlier about the fact that once you raise, let's see here. Oh, the fact that the ceiling joists are carrying tension loads through that roof system. And so we got to make sure that we're connected appropriately at the heel joint where the ceiling joist and the rafter come together so that we can carry that tension load. So for a 30 pound per square foot roof snow load here in table 3.9a, our roof spans 32 feet, so we end up interpolating. And the 7 and 12 roof pitch, and we come across here and we see that we need somewhere between 4 and 5 nails, so we're always going to round up to 5 nails, which is what we show in the table over here on page 28 for those connectors. So again, that's resisting that thrust. Table 3.9 then, if we were to back up a page, gives us the load on that particular thrust connection. So again, if you wanted to use some sort of proprietary connector, table 3.9 would allow you to do that. It's tabulated at 605 pounds. So let's jump to the next page. I want to take a look then at the vaulted ceiling. So this is for that raised ceiling. I'm on the top of page 29 of the workbook. And we've got, again, that 32-foot span, 7 and 12 roof pitch. We end up pulling a value out of the table, but in this particular case, because we've got a raised ceiling, it's got additional load on it. So come back over here to table 3.9a, take a look at footnote 5. It's a very similar footnote to what we saw earlier. Because that ceiling joist is up in a third of the way into the attic space, there's an adjustment factor, an amplification factor there of 50% for that additional load that ends up on that rafter tie. So that's built in here. That same adjustment factor back in the workbook on page 29 applies as well to any loads that are tabulated. So you can see we end up tabulating a value of 681 pounds. For that, and let me back up and see, what was it for the ceiling joist? It was about 600 pounds. So you've got, you know, some additional load there on that rafter tie. Then we talk a little bit already about the blocking to rafter connections or the rim board to rafter connections. So just again, table 3.1 is sort of the catch-all for that. All right, we're going to wrap up here then with a quick summary of the roof story design. And so everything we've gone through now ends up being summarized in these tables. And so we've got for walls 3B and 3A, these are the gable end walls. So they're numbered 3A and 3B because they're on the sort of that third level, I guess. We ended up with a number 2 2x6 that's 9 foot 4 inches long on the attic end of the building. And then on the vaulted end of the building, because we framed studs up, as you'll recall, those end up being second floor studs, we framed those up 12 feet tall. We only needed about a 6-foot stud. You could probably do that easily with 2x4s, but because all the other framing is 2x6, to keep that consistent, we went with a 2x6 in that gable end system. Those are all 16 inches on center. We sized our connectors for lateral and shear loads. So we're showing the loads there, the uplift loads as well, and then the plate to stud lateral loads are all prescriptively spelled out in table 3.1 to make sure we're handling all the loads in the system. Roof and ceiling framing summary here shows the rafter sizes that we ended up with. Remember that vaulted ceiling, we ended up with 2 by 12s at 12 inches on center. The ceiling framing in that vaulted ceiling was number 2 by 8s. And that's 21 feet long, so that's pretty long 2 by 8. So you might end up splicing those, and so you have to account for that and any additional moment because of load, dead load on that splice. So just be careful with any kind of long span like that with solid sawn lumber. That can get a little tricky. So I think we're at the top of the hour. I'm going to ask Marcy if she would to come back and close us out, and then if you want to stick around for some Q&A, we'll ask Lori and Pete to see what kind of questions came in for us.
All right, let me take the screen back. All righty, so our partner organization, Woodworks, they provide some wood project assistance and other resources, so if you want to check them out, their website is help@woodworks.org. If you're looking for wood project assistance, go ahead and give them a shout. And also, if you are a building official, our field staff would be happy to help you. And you'll have an opportunity if you fill out our survey. You can your contact information there, and we'll put you in contact with either Woodworks or our field staff. And then our design professional membership is especially geared toward engineers, architects, and building designers. So if you want some information about that, check out our website, www.awc.org membership. And then we have a special program for Code Official Connections. Go ahead and you can check out some information here or on our website, www.awc.org, Code Connections. And then, once again, just remember you'll be getting a follow-up email today. Give us a few minutes, pull all that information together for you. The survey link, another chance to win a free publication. Look for information about your certificate of information, or certificate of completion, excuse me, and continuing education credits. Note that the actual certificates will be available within 2 weeks of the webinar, not immediately. Remember that in order to receive that credit, you must have been present for 90% of this webinar, which is 54 minutes. Be sure if you are watching in a group that your coordinator fills out that multiple attendee form. And finally, remember our upcoming events. We hope to see you next week, and be aware of our upcoming June 23rd Fire Design for Code Acceptance webinar, and as always, our ever-evolving self-directed study program. Email us at education@awc.org or visit our website at www.awc.org. If you're interested in booking a live presentation for a large group in your organization, please contact us at education@awc.org. That covers my information and reminders, and I'm going to send you back to Buddy for questions and answers.
All right, so Lori, Pete, I see a few questions came in there. Why don't you guys go ahead and tee up what...
Yeah, we had a lot of good questions today. So the first one we're going to bring up, let's see. Okay, here's a good one. Do we have tables for LVLs or other engineered wood products in the WFCM?
Not specifically in the prescriptive chapter. However, once you get into the, let's see, let me see if I can find a good one here. In the engineered chapter, we show a lot of loads. For example, let's look at floor joist framing. Table 2.7c, if you follow along on the screen there, shows floor joist bearing stresses for floor loads. So all of the induced stresses show up there. In 2.7b, the previous table, we show floor joist spans for 40 pound per square foot live load. So we show the required E and bending capacities for those, which means, and I think, let me just see if I can get to I thought there was a table as well, but if you have the capacities that are shown in the catalogs for those i-joist manufacturers, here's the one I was looking for, table 2.8b, floor framing capacity requirements for a 40 pound per square foot live load. We notice we tabulate moment, bearing, and apparent rigidity values that are required. And so you could use those to pull a catalog value out. We do this for various types of members like floor framing, roof framing, etc. So there is a sort of a backdoor approach to incorporate engineered wood products. What's next?
Okay, we had another good question. So if you have rafters and studs that don't line up, you know, for example, if your studs are at 16 inches on center and your rafters are at 24 inches on center, what assumptions do we make in terms of, you know, loads on that top plate, in terms of when the rafter doesn't align with the stud?
Great question. And what I'm going to do there is actually take a look at Table 3 on page 114 of the Wood Frame Construction Manual. And you might think that's a little odd to answer the question this way, but I'm going to point you to our joist span limits of 26 feet and our rafter span limits of 26 feet. So what we've done is we've taken a look at the case where a rafter or a joist falls dead center between two studs below. And we've looked at the bending capacity of that double top plate, and that's a limiting factor in a lot of cases for why we limit spans to 26 feet. So if you want to go beyond 26 feet, you can do that, but you have to address this very issue, and that is either to get your rafters and joists and studs to line up, or you have to design your top plates to handle that additional load. So that's why we have some of these limits incorporated into the wood frame construction manual to begin with. Good question.
All right, and I think we got time for one more. So we looked at the span tables in 3.26, 326 earlier. We had a question come in about which load combinations did we use from ASCE 7 when we calculated those 326.
Great, great. I forgot to come back and talk about that. Actually, we'll spend a little more time on it next week. Since we only took a look at the gable end walls today, we didn't really talk about what we do with load-bearing walls. So let me just touch on that briefly. For the gable end walls, we looked at component and cladding loads only in bending. Now, when we get to the load-bearing walls, we're going to do two checks. We're going to do a component and cladding bending only check, and the tables that you see in the wood frame construction manual, the ones that you referred to, are based on that bending only check, because what the other load combination you need to look at when you look at bending and axial loads, instead of component and cladding loads, you're going to use main wind force resisting system loads. And there's an interpretation we got from ASCE 7 about that the component and cladding bending loads always control within the limitations that we've put on the wood frame construction manual. And I'd venture to say, unless you've got some really heavy axial loads, it's going to control in most cases. So those are the two different load cases we evaluated, but component and cladding loads bending only is what controls, and that's what those tables are based on. So that's a great question, and we'll probably touch on that again next week when we look at those load-bearing wall tables. Anything else, Lori?
I think that's all we've got that we want to dive into today. We're pushing past 10 minutes past the hour as well. So.
Okay. Well, thank you all for being here again today, and we look forward to seeing you again next week when we look at the second story design, and tell your friends to join us. Thanks.